Okay, good. So thanks for the opportunity to speak today. My name is Eddie Schwalbach, and I'm here from the U.S. Air Force Research Laboratory. Work in the Materials and Manufacturing Directorate, and in particular, work with a group that focuses on processing of metals. I'm going to switch gears a little bit from some of the talks earlier that really focused on AM modeling techniques and problems, and talk a little bit about some the measurement and experimental activities that we've been executing under this additive manufacturing modeling challenge program that we've had running for a couple of years. But my hope is that this will be of interest to folks that are developing and testing out AM modeling capabilities. The structure of the talk is pretty straightforward. I've got some background material to provide some context and describe some of the guiding principles we went about while creating this program. And then I'm going to walk through 4 specific challenge problems that we defined and posed publicly, and talk about some experimental activities we executed to generate data sets to support these, both in terms of calibration and input data, as well as data sets that could be used to compare blind predictions against, and kind of summarize some findings at the end of the talk. So I think this won't be particularly controversial, but we view additive as a very enabling technology. The ability to rapidly iterate on designs, the ability to fabricate geometries which are traditionally very difficult, or in some cases not possible to fabricate, is kind of very attractive in terms of a manufacturing process. But there are also some challenges which can also be viewed as opportunities, depending on how you look at it, with this collection of technologies. And most of what I'm going to focus on today is really metallic for sure, and really focused on laser powder bed. But I think some of these statements are general. One of the big, I think, challenges / opportunities with additive is the intricate link between the geometry you're trying to fabricate, the particular details of the processing plan, and we saw a great example of that in the talk just preceding the break, and ultimately the location-specific thermal history, microstructure, and properties that are developed. This degree of coupling and interaction between these different kind of phases of designing and manufacturing a component can present some challenges. And I would say it's a hypothesis that modeling and simulation tools will be very useful in helping to understand these links and design and fabricate successful components kind of within the context of this situation. So in order to both understand the capabilities of current modeling techniques, as well as to get at what certain measurement capabilities and techniques can provide in terms of both input as well as validation data for these types of modeling tools, a group of colleagues of mine at the Air Force Research Lab assembled a series of challenge problems where we essentially asked the modeling community to make blind predictions about various different types of behaviors. After having been provided some information about the details of the processing situation, in some cases calibration data, and the plan for the program was to take those blind predictions and compare them against measured behaviors, and assess kind of where models were functioning, where there were gaps, how useful certain kinds of input data were or were not, in order to develop both the modeling capability and the measurement tools. And we set out to cover kind of the full span from process to structure to properties, though not all in one leap. We did, as you'll see here in a moment, kind of break these challenges up into kind of sub-problems that were essentially independent of each other, so folks could pick and choose the types of problems they wanted to work on. As I mentioned, this really focuses on laser powder bed fusion, and in particular with this effort, we looked at powder bed fusion of iron 625, very common nickel-based superalloy, using a common machine, an EOS M280. As I mentioned, we divided the challenge space into four specific problems along kind of 2 orthogonal dimensions. The first of those dimensions was kind of the length scale of the type of prediction. So we have what I call a macro type problem, which is kind of at the part scale, multiple millimeters and above. or a microtype problem, which would be down at the scale of an individual track in, say, a laser powder bed fusion problem, or even a grain scale type simulation. So that's the horizontal axis in this matrix. The vertical axis is the type of question we were asking, and the first row represents this link between process and structure. So given some information about the process, make some prediction about some structural detail, some microstructural aspect of the material. And then separately, provided some description of the microstructure, make a prediction about the way the material will behave, its properties. We basically broke the link between these two and asked them as kind of separate types of questions. Logistic-wise, we started this program a couple years ago. We really got going in terms of publicizing and publishing the problem definitions in about August of 2019. So the problem definitions, the input data, the calibration data that were provided, those were all published late 2019. Participants had through the end of January 2020 to make blind predictions about the problems that were posed. And then we collected those responses. They were returned back to the folks running the challenge here at AFRL. And right around the time things started to shut down with COVID, March 2020, we were in the thick of evaluating those responses against the empirically observed measurements. And roughly 1 year ago, September 2020, we had a kind of a 4-day workshop debriefing the participants, speaking with folks that made predictions and talking with them about what worked and what didn't work, what kinds of data they wish they had. Again, assessing model capabilities, assessing measurement techniques. We had about 20 different responses across these 4 challenges, and they were actually fairly evenly distributed in terms of the number per challenge question. They were also, interestingly, fairly evenly distributed across business, from large to small businesses. We had a number of universities represented, and we even had some participation from other folks at national labs. Now, what I'm not going to do today is get into the details of the various different responses. First off, there's 20 of them. We would be here for 4 days, right? We had a workshop doing that. It was the better part of a week. But really, my objective today is to kind of give a broad and honestly fairly shallow perspective on some of the data that was generated as part of this challenge. This data has been published. There are a number of articles that either have already or will shortly be coming out in Integrating Materials and Manufacturing Innovation, IMMI. It's a journal published by TMS, describing the data sets as well as describing the responses that were sent back. All the respondents were invited to write an article describing what they did, how their tools work. Roughly half of them or so did end up doing that. So I'll point to some citations towards the end of the talk if folks are interested in learning a bit about those details. But I'm going to pass through this relatively quickly, but what I will say is that there are important considerations about designing experimental and measurement activities that are intended for validation of models. And if I have time towards the end of the talk, I'll kind of walk through some of these guidelines. This is something, there's a lot of literature on this issue, and this is a particular citation. This work by Oberkampf and Roy does a very nice job of, I think, collecting some big picture principles that one should keep in mind while designing this kind of activity. I'll say we did this. We tried to follow these to the best of the constraints we had to somewhat mixed results. I think we did better on some of these than others, and obviously nothing's ever perfect, but certainly these were very helpful things to keep in mind as we were going through this process. So at this point, I'm going to actually kind of walk through each of these 4 challenges. Again, the goal here is to kind of give you a high-level idea of what kind of data was generated and what is available in case folks are interested in using this kind of thing, or possibly in developing their own data sets in the future. So the first of the 4 challenges that I'll describe is at this kind of macro or part scale, and it focuses on the link between process and structure in the context of the prediction of a residual strain kind of in a component. So as we build components, you can develop residual strains, and these can lead to deleterious issues like warping of the part, cracking, in some cases, delamination of parts off of build plates, ultimately build failures. This is kind of a first order problem in many builds. And so a natural question, one of, I think, the first questions that came to mind when we sat down and started thinking about this project was, what is the state of the art in terms of the ability to kind of quantitatively predict the strains that build up in components over time? So we ended up building a series of items and using an energy dispersive X-ray diffraction technique, along with some of our collaborators, colleagues at the Advanced Photon Source at Argonne National Lab, to measure location-specific residual strains in a collection of, I'll say, very simple and slightly more complicated components. One of the basic principles here was to actually work on fairly simple things in this project. We didn't want to go to too complicated of a situation. And so I'm showing a build schematic in the upper left-hand corner here. The highlighted components were part of this challenge. The red items were basically flat walls of varying length and thickness, that were provided as part of the calibration data set. So the residual strains I'm showing in the kind of the top row of images here were measured, and those were part of the problem definition. And we asked for folks to predict the strains that would evolve in these green components, a series of tubes effectively, as well as an L-shaped structure with walls of varying different thickness. So here we provided the calibration data. We've also provided descriptions of the processing parameters, the typical parameters you'd imagine for laser powder bed fusion, and a relatively basic description of the scan strategy. And then ask folks to make predictions for these green parts. So I'm showing on the bottom half of this screen some of the measured, this would be the validation data now, the measured residual strains in these components. And you can see that largely there are very similar patterns, although the asymmetries in the slightly more complicated part are exaggerated. We've, of course, changed the constraints, changed the interactions between some of these components to not put us in a kind of wholly new regime in terms of behaviors that are happening, but certainly pushing beyond, not just interpolating within the calibration data sets. So our second challenge, again, staying at this kind of staying in this process to structure kind of regime, but now thinking at a smaller length scale, we zeroed in on prediction of bead geometry as a kind of a first order indicator of some of the details of the thermal history. Again, the preceding talk gave a nice example of how complexities in the scan strategy can cause variations in the size and shape of the melt pools. And we thought basically looking at the ability to predict those shapes would be a good first proxy for getting ultimately towards a prediction of kind of more details in the thermal histories. So here, the calibration data consisted of measurements of individual tracks that were deposited using different powers and speeds. And then the challenge question focused on multi-track deposits. So if I switch to the next picture, you'll see a build here that actually looks fairly familiar. In the previous challenge, we were focused on some of these walls. I'm now focusing in on a pad that contains a series of single tracks, which are our calibration items. And then the multi-track items, which consist of a block that was built up as effectively a substrate, and then a series of tracks that were laid down on top of that block in a single layer in this case. So we begin to now explore some of the transient behaviors. Again, we're still looking at a very simple scan strategy, but depending on where we section and look at this object, whether we look in the very center of this multi-track or whether we come in and look near the corners where the beam is turning around and the thermal situation is a bit more transient, we can explore a range of different responses in terms of the material. So again, even sticking with simple geometries, you can really begin to kind of push the system into very dynamic situations. This is also an example where we had to be very careful about understanding our measurement technique. We were asking people, particularly when we come close to these turning events, we were asking folks to make predictions about these very transient scenarios. We want to make sure that the measurement planes, for instance, are where we say they were going to be, right? If I'm asking a question about a location 100 microns from a turnaround event, I want to make sure that I'm not actually at 250 or 20. So we used some advanced serial sectioning techniques and fiducial marking strategies to get ourselves to a position where measurements are coming from the intended location to within kind of single micron precision. So again, this kind of thing seems fairly simple, fairly trivial, but quickly can become quite complicated in terms of actually executing the experiment and understanding the uncertainty you have in your experimental data if you want to make kind of a one-to-one comparison with the models. Switching now to the structure to properties type questions and going back up to the macro scale, here the focus was on trying to predict kind of tensile behavior of, I'll call them bulk type structures, given information about the microstructure. So we're not giving processing information anymore. We're not asking people to make predictions about the microstructure. We're basically, in this case, going to define, hey, this is the microstructure that we observed after printing these components. Please make a prediction of what you would anticipate the tensile behaviors to be. So again, we've heard a few times about the effect of kind of location specific variations in the process that can change microstructural features. Looking at things like the thickness of a component, its orientation, and then things outside of the build, things like subsequent machining operations or heat treatments that can modify the microstructure. So here, the calibration data consisted of printed tensile bars. We basically provided the tensile behavior. So you see the stress strain curves for ASTM E8 compliant round machined tensile bars that came from an additive manufacturing build. In addition to characterizing the mechanical behavior, we also characterized the microstructure, and as a kind of a quick pictorial description of that, I'm showing some electron backscatter diffraction maps of the grain structure interrogated on orthogonal planes in a region which is representative of the gauge. But we also provided a number of different quantitative descriptors of the microstructure. This is another theme throughout this series. We typically did provide some kind of summary data, some kind of quantitative information, tabular data, in many of the scenarios I'm describing, but typically also provided the raw data in case various respondents needed some kind of input feature that we hadn't chosen to summarize out of the raw data. So that raw data was made available in case people wanted to do further analysis. So this is the calibration data, and then the actual validation operation. We provided very similar, essentially the same descriptions of the microstructure, but now we're looking at a very broad range of specimen geometries. So we are varying specimen thickness in the as printed configuration. We're varying the orientation of these objects. In some cases, we have as printed surfaces. In other cases, we've removed both the roughness and the near surface microstructure from the specimens. And then we're also exploring a couple of different heat treatments in these materials. So again, the microstructure descriptors were provided, and the request was to predict various aspects of the stress strain behavior. Our final challenge, checking the clock here, number 4, was again sticking with structure to properties, but now moving down to very fine scales, grain scales. Here we're really looking at the response of a particular grain in the material to aggregate loading. So in this experiment, we took a tensile bar that was designed to go into a high energy diffraction microscopy setup at Argonne National Lab in the synchrotron at the APS. This is a specimen that has a relatively small gauge volume. It's about a 0.5 millimeter by a 0.5 millimeter by roughly a millimeter in length. This can be pulled in tension, and you can see on the right here a stress strain curve with some interrupted experiments collected along the evolution of this stress strain curve for this specimen, where we performed at each of these yellow points a diffraction experiment, a near field and far field diffraction experiment that allows us to characterize the microstructure to some extent, but more importantly, the state of strain in the individual grains in this specimen. So we can see basically how the aggregate loading of the specimen is partitioned in various different grains to get at the effect of not just the details of a particular grain's description, but also its neighborhood, what grains surround it. So this experiment, the loading experiment I just described, was carried out at APS. In the beamline, the specimen was unloaded and brought back to AFRL, where we performed a serial sectioning operation to produce a higher resolution, essentially a higher fidelity description of the microstructure. And then a fusion operation was then performed in order to bring together this high resolution description of the microstructure with a grain by grain and stress state by stress state description of the evolution of the elastic strains during this tensile test. This produced a data set that has about 27,000 grains described, considering the grains that are more than about 3 microns in diameter. Of that large collection of grains, we could clearly track 165 of them through all of the loading states, all 7 strain states. And of those grains, about 30, just under 30, 28, I think, could easily and very clearly be linked back to the higher fidelity description of the microstructure that you see on the left-hand side here. So these 28 grains formed the basis of the challenge. The full microstructure was provided as part of the calibration data or input data. The stress strain curve for the whole specimen was provided again as the input data, and then the question was basically what is the elastic strain in any of these individual grains at the various different loading states. So the idea here is to provide some data for characterizing, for instance, crystal plasticity finite element type models of these very local evolution of mechanical properties. So kind of pulling some things together, again, this is a very shallow description of a really broad array of experiments. The data that I just described that underlies these, both in terms of the problem definitions, the input data, and now actually the validation data, has been described in a series of articles as well as being published and made available for folks to use, in addition to the teams that decided to participate in the actual challenge program itself. So broadly speaking, I think we were pleased in terms of the breadth and nature of respondents that participated. We really weren't sure how many people would be willing to go out and try to make predictions, particularly not in a public forum where their performance would be shown for all to see. We were also pretty pleased in terms of the range of modeling techniques. The various different challenges have different kind of technology readiness levels, I'll say. I think challenge 4, for example, would typically be considered a very academic type of problem. Challenge number 1, something much more like what you would see in kind of commercial offerings. But we did actually see a pretty good breadth of both techniques and folks participating. And then the other thing I'll say, one of the things that actually comes back to some of these recommendations about designing validation type experiments had to do with the interaction we had with the participants. Both before we ran the program, we tried to have some workshops and work with modelers to get input about what information would they need, how would they like that to be provided, and kind of squaring that, so to speak, with what could be done in terms of the experimental techniques. As we moved on, we had to kind of separate and have fewer discussions because of the challenge nature of doing this. We did not want to be seen as being kind of too close to any potential participants. But in general, that kind of collaborative interaction, I think, was very, very useful, both for us to understand the needs of some of the models, but also for the modelers to understand what can easily be measured, what cannot be easily measured. So on the whole, I would say that was, I think, one of the most exciting things about all of this. One other message that came through was being very diligent about measuring every single thing that the models needed to within what was practical. There were a number of situations where we just simply could not measure some things, and I would say that was a case where there's a lot of additional uncertainty in the predictions that were made in some cases because of things we just, practically speaking, given time and budget constraints, we couldn't measure. So that's another big takeaway here, is to be really, really careful up front about understanding the importance of various different inputs, even and squaring that with kind of the resources available. Now, this particular program is over. As I mentioned, I'll show some citations here in a few minutes if folks are interested in using the data, but there are other benchmarking activities, other validation experiment activities that are ongoing. Some of my colleagues at NIST have run in the past an additive manufacturing benchmarking challenge, AM Bench 2018, a couple of years ago, and are in the process of running another one right now. So I don't know the accuracy of these dates. This was up on the website the last time I went and looked, but if you're interested in this, I would encourage you to kind of keep track of postings to the website that's shown here for the upcoming round of challenge problems that'll be held in the next calendar year. Again, the breadth of everything I showed clearly requires a large team to put these kinds of things together, both inside the research lab as well as with a number of external collaborators at APS, at a number of businesses and universities we work with. So I'd be remiss if I didn't, at the very least, show you their names very quickly on a slide. There's too many to mention in the time available, but I certainly would not be here talking about this without the inputs of the folks on this page. So with that, I will kind of wrap up. I'm going to put up on the screen some of the citations I mentioned. Again, I'll say integrating materials and manufacturing innovation starting around June this year contains most of these publications, both in terms of the data descriptor articles that go into much more detail on the experimental techniques and the data that's available, to include links to those data sets. And then I'm not showing them here, but many of the participants did choose to also submit articles describing their modeling contributions that would be in basically the same journal edition as the papers that you see here. So with that, I'd like to open it up to questions.
Yeah, thanks a lot for the exciting overview. Mark has already the first question here. Mark, yes.
Okay, thank you very much, Paul. So thank you for the interesting presentation. So in terms of the challenges, and maybe in particular for challenge 4, I was wondering whether the process-related defects would also not deserve a central role. So the microstructure is one thing, but typically the defects, which can be very important for dynamic loading conditions, seem to deserve a somewhat more pronounced role. What was the target there?
Yes. So the serial sectioning operation that I mentioned, I showed primarily the reconstruction in terms of the electron backscatter diffraction description of the grain structure, but we do have optical sections throughout this domain, and those provide a picture into the voids, the various types of porosity that are present in the specimen. So those were part of the description of the microstructure. In terms of the tensile behavior, the aggregate tensile behavior, I don't know how important they were. I would have to go back and ask some of our folks how close the challenge grains we looked at were to some of the pores in the material. Again, I agree for dynamic loading, those items I would expect would play a very significant role. For the particular tensile test, I don't know. And that brings up another interesting kind of issue here. You know, I mentioned kind of the neighborhood. Was one of these challenge grains near a pore or not? What was the closest pore to one of these grains that we selected? The grains that we selected were not necessarily a random sampling of all of the 27,000 grains within the domain, right? They had to meet a number of specific criteria in order to be considered kind of valid. And it's actually an ongoing analysis right now to understand how representative of the global population of grains are those 27 that happen to meet our logistical criteria. But I will take that back to the team and ask about the porosity and whether that can be, how we can quantify that with respect to the challenge grains. Yeah, good question. Thank you.
Thank you very much.
Yeah, thank you.
Okay, Adrian, maybe a quick question.
Yeah, very, very fast. Okay, so thank you for the talk, Edwin. I wonder, you know, you're pointing here to 27 grains or 17 grains, I don't remember exactly, right? I mean, if you repeated the same build, you'll get different grains, right?
Yes.
And so, I mean, was that a set of this data used, or, I mean, I'm concerned about the repeatability and you know, if you cannot repeat it, you cannot model it, right? So
Sure. Yeah. Yeah, I think the objective here with this particular challenge was to get at some of the models that take into account the explicit representation of the microstructure, which can be important for, you know, crack initiation events, things like this that are very, very local. So, but how do you then take that result and coarse grain it, so to speak, to understand, okay, but what does that mean for a population of 100 tensile bars or 100 fatigue specimens, or a component that has many, many more grains in it? That's a very, very valid question. That was certainly outside the scope of this particular challenge, where we were, I think, really focusing on trying to understand whether the models had an accurate picture of the elastic strain in the grains. But it's absolutely essential to looking at how you use that model in the context of kind of a hierarchy of tools that move us to larger and larger length scales, more component relevant length scales. I don't know if that quite addresses the question, but.
Well, I mean, I could continue discussing, but that's good for now. Thank you. Thank you.
Okay.
I appreciate it.
Okay. I mean, okay. Now I'm kind of fighting with myself, but I'm very curious. I mean, what was on average the quality of the predictions that you got? Were the models already quite good in particular challenges, or are we still far away?
I would say it varies quite a bit. I mean, obviously these 4 challenges touch on very different kinds of models, and we saw, you know, a varying degree of quality, from things that were surprisingly good to cases where there certainly still needs to be a lot of improvement. But I will caveat that with statements about the uncertainty in some of the measurements, right? We're to the point in some cases where I think there were some essential pieces of information that we probably need to nail down better. For instance, in the challenge looking at the single and multi tracks, we didn't have a very good measurement of the background temperature of the layer prior to depositing the tracks. So I think that inhibited the ability of some of the models to make very good quantitative predictions. Although qualitatively, I think we were fairly impressed with the trends that these tools were able to predict. So in terms of a short answer to your question, it's difficult because it was quite variable. And it also depends on how you plan to use the model, right? If you really do need to know absolutely the particular value of residual strain in a grain versus qualitatively, do I expect a 5% change in the melt pool size or a 50% change in the melt pool size? You know, the answer to the question changes, I guess.